Why do hot objects glow? Whether it's molten iron or a candle flame, many materials end up in a similar pattern. First red, then orange, yellow, and white. Why do hot objects emit light at all? And why can't they just heat up without glowing? If something absorbed energy continuously, without releasing it, it would defy the laws of thermodynamics, so it must radiate energy away. This behavior is explained by blackbody radiation, where an ideal object absorbs all incoming energy and then re-emits it, with the color determined solely by its temperature. While no real object is a perfect blackbody, this approximation works for our purposes. In this video, I'll show you how to incorporate this principle to color fire in your game. Our eyes see colors as a mix of different wavelengths. To figure out which wavelengths a hot object emits due to blackbody radiation, we use Planck's law. Given a temperature and a wavelength, it tells us the emitted brightness at that wavelength. We only need to worry about wavelengths from about 380 nanometers to 780 nanometers, since that range is visible to the human eye. The formula uses degrees Kelvin instead of degrees Celsius. The difference is that in degrees Celsius, 0 degrees is the freezing point of water under standard conditions, while in degrees Kelvin, 0 degrees is absolute zero, the lowest possible temperature. To convert Celsius to Kelvin, just add 273.15. Now we know the brightness at every wavelength, but the human eye and your monitor works in terms of red, green, and blue, rather than a continuous spectrum. We need to determine how strongly each wavelength stimulates the three color cones in our eyes, and fortunately, this has been measured experimentally. We can look up each wavelength in a reference table, such as the CIE 1931 2 degrees standard observer, and convert those values into the XYZ color space. On the screen, you can see three curves, X bar, Y bar, and Z bar, that represent the responses of your red, green, and blue cones respectively, to any given wavelength. Sampling these curves at a wavelength produces a XYZ value, which identifies a color in a space of all possible colors your eyes can perceive. Also, on the screen you can see the CIE chromaticity diagram. The horseshoe-like shape with various colors inside represents the XYZ color space. These are all the colors your eyes can detect. Note that the labels X and Y on the axes do not refer to the X and Y components in XYZ. The sRGB triangle inside represents all the colors your screen can display. Since your screen cannot display all the colors your eyes can see, especially those with higher saturation, we need to convert the XYZ value to a linear sRGB value to display accurately. And unfortunately, some oversaturated colors may be clipped. Modern displays may support wider color spaces than sRGB, but not all monitors and game engines support them. So I'm just using sRGB. The conversion from XYZ to linear sRGB is accomplished with a matrix multiplication, using the matrix defined by the sRGB standard. Without this conversion, your fire will look wrong, and be only yellow as shown on screen. This looks nothing like the fire shown in the beginning. Computing a black body's emission spectrum using Planck's law and converting it to a sRGB color for every pixel, every frame, is expensive. To avoid this, we can pre-compute a gradient texture. First, choose a temperature range. For example, from barely glowing at 600 Kelvin to extremely bright at 60,000 Kelvin, which is just above the temperature of lightning. Realistically, interesting color changes happen between about 1000 Kelvin, which looks red hot, and about 10,000 Kelvin, which looks blue-white. Above that, the color stays bluish even though brightness skyrockets. We can use exponential mapping on the texture coordinates to allocate higher resolution where colors change more quickly. This means we remap the normalized temperature values using an exponential function, stretching the scale in regions of rapid color transitions, like between 1000 Kelvin and 10,000 Kelvin, and compressing it where changes are minimal. By doing so, changes in color will be distributed more evenly throughout the texture, and not clumped at the start. Looking at the graph of the exponential function, you can see how it redistributes the temperature values. In the low temperature range, the graph grows slowly, meaning more samples are taken there. When the graph grows fast at high temperatures, Each pixel in the texture increases by more and more temperature values, thus giving the higher temperatures less samples. Next, we store this gradient in a small 256 by 1 texture, which is so small that it can fully fit in the GPU cache, and is thus cheap to sample. At runtime, all you need to do is pass the degrees Kelvin temperature value to the shader. Use a function to convert it to a texture coordinate, and sample the gradient texture we just computed. Hot objects become extremely bright very quickly. According to Planck's law, doubling the temperature multiplies the energy emitted by 16. Without tone mapping, super bright colors will oversaturate or clip on screen. A tone mapper like ACES compresses the intensity into a monitor's displayable range, preserving detail and making bright colors appear natural. Without it, bright yellows and reds turn to primary colors instead of desaturating towards white. ACES tone mapping compresses the dynamic range of light into the limited range of your display. There are other tone mappers like AGX, but for this demo, it is easier to see the color changes in the flame using ACES. Changing the tone mapper setting can sometimes drastically alter how the scene looks. For the best results with realistic colors and brightness, it is important that other elements in your scene also use physically plausible brightness values. We've talked about mapping temperature to color, but how should temperature itself change over time? Real objects don't cool linearly. Instead, they lose heat quickly at first, then cool progressively slower as they approach ambient temperature. Newton's law of cooling accurately describes this behavior and provides realistic results, so it's the correct choice to achieve realistic-looking fire. At first glance, linear cooling may appear similar to realistic cooling, but only if you manually adjust it to match Newton's law of cooling. Here, I've intentionally tweaked the linear cooling results to closely match Newton's law of cooling ones, which required extra parameter adjustments. However, when we compare them directly without artificial adjustments, linear cooling clearly falls short. Notice the unrealistic abrupt color shifts and unnatural cooling behavior. In contrast, Newton's law naturally provides smooth and realistic transitions from bright colors at hot temperatures to darker colors at lower temperatures. Newton's law of cooling has 3 parameters: starting temperature, which represents the initial temperature of the fire. Realistic values for campfires range approximately from 600 degrees Celsius for small fires up to around 1100 degrees Celsius for larger bonfires. I use the higher value to have a wider range of colors, but campfires are more red and orange and don't go as bright as mine. Next, ambient temperature is typically the surrounding air temperature, is set at around 20 degrees Celsius, which is room temperature. Changing this value makes little difference, with values of plus or minus 100 degrees beginning to make a difference, with larger values creating more noticeable visual differences. Lastly, the cooling rate constant K determines how quickly an object cools towards ambient temperature. Realistic fires have values around 0.3, but exact numbers don't matter for graphics, as long as it looks right. Here's how changing the cooling constant K influences your fire visually. Notice how higher values of K cause faster cooling, rapidly transitioning between colors, whereas lower values produce longer, smoother cooling transitions. Changing K gives you the flexibility to simulate different materials or environmental conditions realistically. Even small changes significantly affect the fire's look, so compare against the reference when adjusting for different materials or conditions. By using Newton's law of cooling, you eliminate unnecessary tweaking and get consistent, physically correct results every time. Once you have your gradient texture, integrating everything in Godot is straightforward. I'll show you the code additions to your shader, assuming you already know the basics. The full project is available in the description. First, in the environment node, set the tone mapper to ACES, so the bright colors of the fire look correct. Next, you need a method for the fire shader to determine a particle's age to calculate its temperature over time. In display, color curves, color ramp, set a color ramp from black to white. There may be a direct way to pass this from particles that I'm not aware of. Alternatively, you can modify the particle process material to handle Newton's law of cooling for customized starting temperatures or cooling constants. The fire shader has been adapted from Godot's standard material 3D shader by clicking Convert to Shader Material and adding the temperature logic. The new uniforms are Texture Planck's emission, which is a temperature gradient texture that we just pre-computed. Make sure to set the compression mode of the texture to lossless, since the texture is very small and lossy compression may decrease the quality. Also, make sure to disable emit maps, since this is a lookup texture and is not directly mapped on a mesh. Planck's emission temperature Celsius sets the initial emission temperature in degrees Celsius. Planck's emission energy scales the final emission intensity. Godot doesn't explicitly document the units used for the emission shader variable, so I'm not sure which value is physically accurate. 0.1 looks right visually, but you should compare brightness against other objects in the scene and against reference images to get the best result. Temperature cooling rate specifies the cooling rate constant used in Newton's law of cooling. Use color as age when enabled. Uses the particle's color as its age. Disable this for meshes and control Planck's emission temperature Celsius externally, based on game events. Two helper functions are added. Unmapped temperature converts the temperature between the minimum and maximum to a normalized 0 to 1 range, using inverse exponential mapping. Then samples a gradient texture for its color. Temperatures below the minimum return black to avoid weird behavior. Calculate cooling temperature uses Newton's law of cooling to compute the current temperature as it decays from the initial value towards ambient. In the fragment function, after processing properties like albedo, metallicity, and roughness, the emission color is computed by calling calculate cooling temperature with color.x times 2, where 2 represents the particle's lifetime in seconds as a time parameter. Passing the resulting temperature to unmapped temperature to obtain the corresponding RGB value from the gradient texture, which serves as the emission value. Although 2 might be expected as the particle's lifetime, it's actually 1 in this particle system. I use this value so that the particles don't disappear when they stop burning, but transition into smoke. Depending on your artistic vision, you might have just fire, separate smoke particles, or a smooth transition between the two. You can set the smoke color by changing the albedo. The values in this code are a starting point. Experiment and adjust them as needed, even if they aren't physically accurate. The Python script for the gradient generator, the gradient texture, and the Godot shader are provided in the description. That's it. Now you know why hot objects emit colors, and how to generate and incorporate them into your game.